Right, here are some questions to get you thinking about equipotentials and potential. So once again, have a good read, pause the video, do the questions, and then unpause. So in question 2, this V here is the potential of the, I can't select it, the right hand plate. This V here is the potential of the left hand plate. And we're thinking about moving from these 4 different corners, A, B, C, D. So pause that now. Right, hopefully you paused it and you've had a go at these. Let's have a look at the answers. So, number 1, sketch the equipotentials in this uniform electric field. Well, let's just get a feel for what's going on. If we take our positive test particle, okay, then the force it's going to experience is from this end to this end. So this is the positive, this is the negative. That doesn't really make a huge difference, but it's just good to think about. Now, equipotentials. Well, it's a uniform field, so the equipotentials are going to be evenly spaced lines or planes. And if we think about the energy changes, the potential energy changes, when we move this way from positive to negative. It doesn't change if we move this way across the field lines. Now this isn't something I mentioned, but it's worth bringing up now, that the equipotentials are at right angles always to the field lines. So if I start drawing in my equipotentials, which you can have at any spacing as long as the spacing is equal. There we go, there's the equipotentials. You'll notice no matter what the shape, that the equipotentials are always at right angles to the field lines. So for this one you want equally spaced vertical lines. It doesn't really matter what the spacing is as long as it's equal. Those would be the equipotentials. Moving a charge along those equipotentials would not change its potential energy. Only moving it this way between the plates would change its potential energy. Okay, that's that one. Next one. How much work is done moving an electron around about the place? Okay. So this is like the plus, this is like the minus, as before. Now we're thinking about an electron which is negative. And we're going to be thinking probably about using the idea that the potential is the potential energy per unit charge in this case, which is also going to be the work done per unit charge moving this electron around. So, firstly we've got to decide if any work's going to be done at all. And in this case, moving from A to B, it looks like work is going to be done. And not only is work going to be done, but it's going to be done by us, because we're having to move this electron towards the negative and away from the positive. Okay, so the amount of work done, if we rearrange this, the amount of work done is going to be V, the potential or change in potential, times Q. We should probably chuck some deltas in here. So the work done is going to be the change in potential times the charge. So here the potential has changed by 10,000 times the charge on an electron, 1.6 times 10 to the minus 19, which is going to be 1.6 times 10 to the minus, we've got 19 there, and we've got a 10 to the 4 there, so it's going to be minus 15 joules. That's the amount of work we're going to have to do. Okay, what about moving it from B to C? Well, from B to C, that's along an equipotential, so there's no work done at all, so that's easy. So we've got 1.6 times 10 to the minus 15 joules, 0. Now from C to D, the field here is doing work on the electron. If we let this electron go, it would be accelerated across the gap. Okay, the field will be doing work on it. Now the amount of work done on it by the field is going to be exactly the same as our calculation in the first part, except because the field is doing work on it for us, we'll call this minus 1.6 times 10 to the minus 15 joules. And finally, from D to, it says from D to E. There is no E. It should say from D to A, of course. From D to A, the work done is 0, again, because it's moving along an equipotential. Interestingly, I've just thought of an extra question. What about moving from A to C? So if we moved it from A to C, have a think. Pause the video again and have a think about how much work you think would be done in moving an electron from A to C. So pause now. Okay, hopefully you've at least given that a bit of thought. Let me just rub some of this stuff out so we haven't got so much confusing stuff on the board. Now it turns out that in an electric field like this, or in a gravitational field, it doesn't really matter what route you take from start to finish. Okay, the energy change is the same. So it doesn't really matter how we get from A to C. The change in potential energy is going to be the same, because the potential energy only depends on the position. That's kind of the definition of potential energy. So if we wanted to go from A to C, we could move along an equipotential, which means no work is done, and then along here, except we'll do it the other way around, because we've already got A to B. So we go A to B, we do this much work, then we do B to C, we do this much work. So the work done going from A to C is exactly the same as from A to B, which is 1.6 times 10 to the minus 50 joules. Voila, hopefully that was useful.